Hello, Chemistry 1A students. Here is your Day 2, Chapter 5 notes. We're going to start at the atomic nucleus on your outline and go through and finish the atom. So again, you should have your textbook out, or not your textbook, sorry, your outline out and in front of you, and be ready to take notes. So starting with the atomic nucleus. So remember that we had kind of wrapped up by talking about Dalton's atomic theory, how we came to know what we know about the atom. So at the point where we stopped, we knew about protons and we knew about electrons. So now that scientists know about protons and electrons, kind of the next part of that was that they wondered how the particles were put together in the atom. Okay, so now that they knew that particles or atoms did indeed have smaller pieces inside of them, protons and electrons, they started to wonder then, how is it that these already tiny atoms that we can't see possibly can have protons and electrons inside of them? How are those protons and electrons organized? So we ended the first day by talking about J.J. Thomson, and he came up with an atomic model. His atomic model is called the plum pudding model. And his model says that the electrons are stuck into a lump of positive charged material. And so that's what he thought. He was trying to picture what an atom would look like. And he knew that there was this positively charged part inside of an atom. And so he said, well, okay, this positively charged part has these negatively charged electrons stuck into them. And he thought that these electrons are evenly distributed throughout an atom that is filled uniformly with the positively charged material. Now, again, back in the late 1800s, early 1900s, when Thomson was doing his work, calling it a plum pudding model was useful because people were familiar with plum pudding and they had eaten it. My guess is none of you know what plum pudding looks like. So I typically refer to Thomson's atomic model as a chocolate chip cookie. Because pretty much all of you have probably either seen or eaten a chocolate chip cookie before. So this idea is, right, in a chocolate chip cookie, we have the cookie dough itself, and then we have the chocolate chips, okay, in that cookie dough. So that cookie dough represents, okay, that positively charged material, right? So that's our cookie dough. And these electrons are evenly distributed throughout that cookie dough, okay? So these are our chocolate chips, okay? right? And if you've done a good job of mixing up your chocolate chip cookies, your chocolate chips are pretty evenly distributed throughout that cookie dough. So this was what Thomson thought that the atom looked like. He thought that inside this atom, it was filled with this positively charged material, and evenly distributed throughout that positively charged material were these negatively charged electrons. Okay, so that was Thomson's model based on the information he knew. So Ernest Rutherford comes along. Ernest Rutherford lived from 1871 to 1937. And he's credited with having kind of done this work in 1911. He wanted to test that model, okay? So Ernest Rutherford wanted to test the plum pudding model that Thomson had come up with. So, again, if he's going to test something, he has to design an experiment. So he designed what is known as the gold foil experiment, where he used alpha particles and alpha particles are a helium atom that has lost two of its electrons and has a positive 2 charge because it has 2 protons left. Okay, so he's going to design this gold foil experiment, and part of the gold foil experiment is he's going to use alpha particles. And alpha particles are, again, that helium atom. It's lost its 2 electrons and it has a positive 2 charge because it has 2 protons left at it. Okay, so he's going to take a narrow beam of these alpha particles and he's going to direct it, so he directed it at a very thin sheet of gold foil. So basically, he's using these alpha particles to shoot the gold foil. Again, he's a scientist, okay? So he's designed his experiment and he's going to say what he expects the results to be. So he says if the plum pudding model is correct of an atom, if we have this positively charged matter with these negatively charged electrons evenly spread out throughout it, then he predicted that the results, should be that these alpha particles pass easily through the gold foil with maybe a slight deflection, because maybe they're a little bit deflected by this positively charged material, because remember our alpha particles up here, these alpha particles, they have a positive charge. So he says maybe they're going to be deflected a little bit. So take a moment and think why. So why would he predict that? Right, he predicted that because, again, he had this idea, and you need to have this in your notes, right? He had this idea. The model said that I have positively charged material with electrons spread throughout, so I expect that these alpha particles are going to go through those atoms And maybe they'll have a little bit of deflection because most of the atom is positively charged and I'm shooting something with a positive charge, these alpha particles, at it. All right, what were his results? Okay. Most of the alpha particles went straight through. Or they were slightly deflected. And leave yourself kind of a spot to put a Y for that. Okay, so that's what most of the particles did. However, a small fraction of these particles bounced off the gold foil at very large angles. Again, we're going to put a kind of Y. And some of these particles bounced straight back toward the source. Now, again, remember, he'd already made a prediction. His prediction was that these should go straight through with only a slight deflection. So, this first little bit here, right? This is what he predicted. So that would be consistent with the plum pudding model according to him. However, the problem is that's not all that happened. He had these particles that bounced off the gold foil at a very large angle. So if you kind of picture this gold foil, kind of being straight here, what is happening here is as we shoot these alpha particles in, okay, they hit this gold foil and they come off at large angles. He wasn't expecting that. And he said some of them, these alpha particles came in and they bounced back. Now, there's an interesting quote, okay, about how surprised Rutherford was by these second and third results that he had not predicted. Okay? It was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. A way for us to kind of think about that is, here's what he really was expecting, right? And think about like your everyday experiences. If you shoot a cannonball at a barn, what do you expect it to do? You expect it to go through the barn, right? That's what he was talking about up here, okay? However, if you shoot that cannonball at the barn and it comes through the barn, but 5 feet later it hits the ground because it's deflected, that's not what you expect. And worse, the most surprising, imagine shooting that cannonball at the barn and it hits the barn and it bounces off of it and it's coming right back at you. That's what was happening down here. So he said, hey, based on this idea of the plum pudding model, that cannot explain what's happening. So he's got to come up with kind of why. So let's kind of talk about the why for why it would bounce back. Remember, I'm shooting something that has a positive charge. So if it hits it and it bounces back, then it must have run into something with a positive charge. That would explain why it might hit the gold foil and bounce back and come right back at me. So he said, okay, if that's what's happening, well then what is happening when it comes off at these really large angles? Well, what if instead of kind of running into it head on, what if it just passes near? So it passes near something with positive charge. And it's kind of pushed away. Okay, that's fine. I'm working, right? I'm starting to get this idea that there's something inside this atom that has a positive charge that these alpha particles can run into. And sometimes if these alpha particles get kind of close to it, but they don't quite hit it, they're really deflected. Well, then what is happening up here? Why did most of them go through this gold foil with straight through or with just a slight deflection? Well, maybe most of the atom is empty space, right? It's not running into anything. That's why it can go straight through. That's why it's only slightly deflected. It's a long ways away from that something with a positive charge. Okay? So, based on that, okay, Ernest Rutherford has a new theory. He has a new way to describe what that atom looks like and how it's organized. And he says that the atom is mostly empty space, all the positive charge and almost all the mass are concentrated in a small region with enough positive charge to deflect those alpha particles. He calls this an atom is described as the smallest particle of an element that retains or keeps its identity in a chemical reaction. Okay, so it's that smallest piece that stays an atom, stays the same. No matter the size of a sample of element, all the elements have the same properties because they are made of the same kinds of atoms. So it doesn't matter if I have a tiny, like thumbnail size sample of elements, or if I have 1,000 pounds of it. Those elements are still going to have the same properties because they're made of the same kinds of atoms. Individual atoms can be seen today, so they are observable with instruments such as a scanning electron microscope. Now, this is not even a type of microscope that most colleges and universities have, okay? So this is not something that's readily available, but if in biology class you've ever seen a picture of a virus, that would have been done with a scanning electron microscope, okay? So to give you kind of a perspective on this, 100 million copper atoms lined up side by side. So imagine taking 100 million copper atoms and making sure that they're like a single layer and they're all standing right next to each other. So like almost as if you were thinking about people, it'd be like people standing shoulder to shoulder. Okay? If we take 100 million copper atoms and we do that with them, we get a row of copper atoms that's 1 centimeter long. A centimeter, a good estimate for a centimeter, okay, is the width of your pinky. It's usually about a centimeter. So imagine taking your pinky and slicing it into 100 million pieces. Ouch. But that's how big a copper atom is. And a copper atom is kind of in the middle of the periodic table in terms of size. Okay? So the idea here, the part of what I want you to kind of come away with is we can't see individual atoms. We're going to talk a lot in class about what protons look like and electrons and neutrons and atoms, and it's going to sound as if we could see them. But we can't see them. We're just kind of picturing them in our head. We're kind of having a model for them. But they're not big enough that we can see. Not even with the kind of microscopes that we would have at the school. So that brings us again to a good spot to stop. You don't have any homework again, so enjoy your day. I will talk with you tomorrow.